right, we are ready to get started. Sorry for the little bit of delay, but we're all here now. So welcome to the NVM Express JBOF session. We're here to talk about boxes containing flash and how those are used in the industry and different ways that you can do these. So I'm going to start out by introducing our panel. To my left here, we have Nishant Lodha, who is the product marketing manager for Marvell, previously Cavium, previously QLogic, the Ethernet NICs and Smart NICs business. We have Peter Anufric, who is from Microchip and Microsemi. He is a fellow in the Data Center Solutions business unit, responsible for architecture and validation of storage products. He is a board member of NVM Express. We have Fazil Osman here to my left. He is a distinguished engineer in Broadcom's Data Center Network Connectivity Group, has a long history of a whole bunch of Ethernet products, so a lot of expertise there. And then down on the end, we have Sujoy Sen, who is a senior principal engineer at Intel's Data Center Group, working on server I/O technologies and focused on I/O disaggregation as part of the rack scale design team. My name is Brian Calgar. I'm VP of Sales and Marketing at Kazan Networks, and we will trade off through this presentation through our various sections. So the agenda today, we're going to spend about an hour here now and leave some time for Q&A at the end. We'll start out with a market overview. We'll talk a little bit about composable infrastructure, which is one of the applications of JBOFs. Then we'll go through a couple of different architectures for JBOFs that are available in the industry now. One is a PCI Express or direct attached JBOF. The other is a fabric attached version of that. And then we'll finish up with some management options on how you use these in that composable infrastructure, talk about some of the remaining challenges, and then again, finish up with Q&A. So with that, I'll turn it over to Nishant to kick this off.
Thank you, Brian. Hello, everybody. Good afternoon. So what I'm going to do is, like Brian said, kind of start off by talking about some high-level storage trends as to what do we see kind of going on within the storage industry. I'm not going to focus on talking like specific to NVMe and things like that, but you hear that all around already through the keynotes and things like that. Let's take a little bit higher level picture and see what's going on now. Within the enterprise, storage spend is growing, and we realize there is more and more data being created, and we need places to store them. So, which is a good thing. And the market last year was standing at $42 billion a year, is growing by a little bit of 2020 to $47 billion. And I'm only talking primarily about enterprise storage here, and that's primarily being driven by all the scale up architectures going scale out, driven by the new architectures that the hyperscalers are defining and enterprises are implementing. If you dig a little bit deeper down within this overall storage growth, growing from $42 to $47 billion in the next couple of years, if you look at only the ECB market, and the ECB, as I define, is the external controller-based block storage market, which today is, you can primarily equate that to all-flash arrays, traditional hybrid arrays, and hard disk-based arrays. That market is pretty flat. Sitting at $25 billion. And there is some reasons for that, and I'm going to talk about that a little bit. Within the ECB market, although I do say that the market is relatively flat, the all-flash array piece of that is showing significant growth, right? And that's no surprise here with almost 26% CAGR and a corresponding decline in the hard drive side of enterprise controller-based block storage business. Okay. So why is all of this happening, right? So a lot of traditional storage deployment models are changing, right? From typical proprietary siloed architectures, things are changing, either moving to hyper-converged infrastructure, converged infrastructure, more software-defined storage, and people are bringing out services farther and farther away from the array into software, into applications, into infrastructures, even into networks. For that matter, a lot of DAS is changing, moving to JBOFs, FBOFs, and then beyond that, you also see that there is certainly NVMe all across, right? A more efficient protocol, and we expect that in the next couple of years, we will hit the almost 50% crossover mark, where NVMe becomes more widely deployed than SCSI. And when I went to college, I studied SCSI in going through my engineering school, and I thought SCSI is always going to remain around, but in very short few years, there has been a significant competition from NVMe that in the next just a few years, we will see a 50% crossover. That I don't remember any other legacy dominant technology being overcome in that short period of time. Certainly with NVMe comes NVMe over fabrics. There's a plethora of fabric options that I'm going to talk about, and definitely 3D Point. But overall, if you look at from the cloud storage market, storage in the cloud is also growing. But there is coming a time where enterprise customers have already moved a significant portion of their storage off to the cloud. Whatever they think they could move to the cloud, email, collaboration, file shares, things like that. But the rest of the data is becoming harder and harder to move to the cloud. Right, there are concerns about privacy, there are concerns about cost, life cycle of that data. So I personally, this is just my opinion, I don't expect the same ramp, what we have seen in the last couple of years in terms of enterprise storage specific moving to the cloud to continue forward, but we'll have to see about that. So fabrics play a key role in moving from JBOFs to FBOFs. And I want to point a little bit of history, right? All of you guys know JBODs, right? They have been around, just a bunch of disks, always served a purpose of giving more storage than a server can consume, not just consume, just get attached to or get connected to. And typically these JBODs were attached by SAS controllers or SAS expanders, and that has been a model pretty much moving forward with JBOFs, where flash comes in, but pretty much the similar connectivity remains going into servers. So there's still SAS connectivity, although inside the box there is PCIe switching, and other people will talk about that in a little bit more detail. What I expect this moving forward is that the SAS connection that you see on the left-hand side will likely change to a fabric-specific model. And we will, within this panel, kind of debate in front of you what those various options are. One of the fabrics could be PCIe, and a JBOF could be directly attached to a server. And in fact, that delivers the best performance that you can get out of a JBOF or FBOF. But there are times and use cases where you want to share FBOF across multiple different servers, and then perhaps it's harder and harder to do with PCIe, although the other panelists will try and present cases on when it is possible. So when let's keep PCIe to one side, right? That definitely delivers the highest performance when connecting to just a bunch of flash from servers. But what are the other networks? If you want to scale NVMe further and deeper into the data center, you have a bunch of network connectivity options, which is NVMe over fabrics. And there is plenty of options around there, and more the options, more the confusion, right? As you can see on the chart on the right-hand side, there is, 7 of those, right? And the earliest one was definitely RDMA, with Rocky as well as IVOR becoming standards a couple of years ago for scaling out NVMe over fabrics. Then came Fiber Channel. That happened sometime last year, if I remember right. There is work going on for FCOE also as an option for scaling out NVMe over fabrics. I haven't found a convincing use case to convince myself on that FCOE has value for scaling out NVMe, but if you guys find something, let me know. NVMe over TCP is something new, right? Something new and very exciting, talked about in multiple different sessions at Flash Memory Summit this year. And what NVMe over TCP is slightly different, although it is not yet a standard per se. I believe it's working through the standardization process and should happen sometime this year or early next year for that. I'm going to go a little bit more deeper into NVMe over TCP. But before that, like I said earlier, one of the most popular considered fabric for scaling out NVMe is RDMA, right? And within RDMA, more specifically, it is Rocky V2. And a lot of you guys, if you have deployed Rocky V2 at scale, you'll understand that there are some challenges with that network, right? It is not kind of built for everyone. It is not. It requires some specific skill sets, and let's talk about what those are, right? One thing to understand with Rocky is that, or Rocky V2 is based on UDP, right? It does not have an end-to-end congestion control mechanism, right? In addition to end-to-end congestion control mechanisms, Rocky can and mostly requires a lossless network, which a customer's fabric needs to deliver. Otherwise, there could be challenges with the Rocky's operation. And this time, we are not talking about HPC-style small message passing. We are talking about storage, right? And customers care about their storage. Storage is near and dear to the heart. When they put bits out on the wire to transport, they want to make sure they get there in time and not get dropped because there are network issues. So the Rocky guys, yes. Okay. The Rocky guys have, the Rocky IBTA along with other organizations have worked hard to kind of bring efficiencies in managing congestion for Rocky and their algorithms like DCQCN, but they are not automatic, they're not precise. You need to tune it for every different environment, and that can pose challenges. We talked about keeping the network lossless in order to enable Rocky. Also, applications need to be kind of ported over RDMA. People require some OFED and verbs expertise. And within RDMA, again, there are multiple camps. There is Rocky V2, there's iWarp. They don't talk to each other, right? But we have definitely determined that we need two high-level options for scaling out NVMe, right? Either it's PCIe direct attached to a server, or it's some kind of fabric, right? And within fabric, there are multiple options. There is a new option that I would like to talk about, which is new this year, is NVMe over TCP. And what is this? It's the new defined binding going through the standardization process where it is possible to scale out NVMe over TCP. And TCP is a protocol that you guys and your customers have trusted for years, right? Or decades, if I should say. It is being promoted by a lot of cloud vendors because a lot of these cloud vendors do not want to do either a full rip and replace in terms of bringing RDMA into their network, or don't have don't want to go about and manage RDMA. The big thing with TCP for NVMe over Fabric is that you can leverage your existing network. If you have older servers, which are your clients, they have 1 gig E, they have older 10 gig Ethernet NICs, which don't understand RDMA, they can still still do NVMe over TCP using a simple software mechanism. While I do believe that on the storage array side, on the hardware side, on the JBOF, on the FBOF side, you do need some kind of TCP offload because that's where everything fans in, and you need the efficiencies that the compute in such a box cannot provide. Okay, off back to Brian.
Thank you very much. Yeah, so let's, that's a great overview of all the different choices of protocols. Let's pull it up a little bit now and talk about how to use JBOFs in one of their applications, which is a composable infrastructure. So if we look at the big web giants, the hyperscalers, the guys that are building, multiple data centers of 100,000 servers each, not all of them, but most of them are generally deploying this so-called shared nothing model. You take a server, you have a certain number of CPU cores in that server, and you add in some storage, some number of SSDs. This is a model that's clearly working. One cannot fault the success of Microsoft and Google's and Amazon's data centers today. But it's not to say it's not without challenges and can't be improved a little bit. So with this shared nothing model, at the time that you build and deploy that, you have to make a decision of how much storage I'm going to add into that particular server. And typically, that's made by looking at your worst case application's requirements for storage, maybe throwing in a little bit extra for the applications coming down the road that you haven't yet anticipated. And then you're locking in that compute to storage ratio for that particular server. It's very impractical to go around a data center of 100,000 servers and be popping in and out SSDs on a dynamic basis. So if we take this shared nothing model and we map a couple of pretend applications onto this, let's say application A requires a SSD and B requires a couple and C requires 3 SSDs. So you can see that these green utilized SSDs are doing their job, and that's all well and good, but there's all these yellow not utilized drives present in those chassis. That's got an industry term now called dark flash, and it's a inefficiency associated with this particular model that represents an opportunity for improvement. The net utilization in this very simple model is 6 out of 12, or about 50% for the storage utilization here. The industry average varies all over the place, but I think 40% storage utilization with this kind of a model is generally accepted out there. So that's certainly some low-hanging fruit and a great opportunity for improvement. So if you want to minimize your dark flash, one option is, well, let's build specialized server configurations for these different applications. And that's, obvious how you do that. You just build a specific model for a specific application. You eliminate the dark flash in this case, but you've really limited your agility, your business agility to adapt to new storage requirements from new applications or changing application requirements, because you don't have a universal set of servers now throughout your data center that you can run any application on. So the idea is, what if there was a way to minimize dark flash and not only retain your level of business agility, but maybe even improve upon it? And that is the disaggregated data center. Everybody's been talking about this quite a while now. Very simply, it's just, let's separate physically the compute side of these servers from the storage side of these servers. We'll create a pool of compute. We'll create a physically separated pool of storage. This is where JBOFs come into play. So JBOFs now are how you house, power, cool, and access these SSDs in this pool on the right. So if we take this idea of a composable data center, we map those same 3 applications back onto their respective SSDs, everything's up and running again, even though they're now located in physically separate spots within your data center. We still have our 6 SSDs that aren't being utilized, so at this point, nothing has changed. But the key here is this gives us an opportunity to do a huge optimization, which is to minimize the size of that spare SSD pool. Okay, so instead of having 6 out there, let's have 1 or 2 as spares for failures, as expansion for future applications as they come along. You're minimizing your dark flash. You're buying fewer SSDs because your storage utilization has gone up. That's CapEx savings. You're powering fewer SSDs. They're not sucking up power even though they're sitting there just idle. That's OpEx savings. And there's other benefits, like you can dynamically allocate from a new application to 20 SSDs if that's what's required. You can chop up pieces of SSD and share one SSD across multiple applications. So you get a lot of business agility. You can upgrade the SSDs independently from the processors because generally those are on 2 separate life cycles. All right, so that's one use for the third platform hyperscale guys that a JBOF can be used for. Now let's go into a couple of different JBOF architectures.
Hi, my name is Peter Newford from Microsemi, and I'm going to talk about PCIe NVMe JBOFs. When people think about PCIe, they think about NVMe, and they think about direct attached SSDs. But you can use PCI Express as a JBOF technology. So let's take a look at, how do you build a PCIe JBOF? It's actually pretty simple. You take a big PCI Express switch, you put it in a box, you put a bunch of SSDs connected to it. You then cable that PCI Express switch to a server. You probably have an SI problem going from the server backplane all the way to the SI switch. So you need a retimer or another switch card in the server. And that's about it. So this is a block diagram of PCIe JBOF. And on the right, here's a picture of the Facebook Lightning JBOF, which is basically just that. It's basically a big PCI Express switch, a bunch of NVMe SSDs cabled through a PCI Express cable to a host. One of the questions that comes up when we talk about PCIe JBOFs is, how do you manage a PCIe JBOF? So let's get through the simple stuff first. First, PCI Express switches don't require management. Switches have been around now for 18 years, and you just plug them in and they work. The OS manages the actual switch itself. So if all you want to do is take a bunch of SSDs and expand your capacity in a server, you don't really need to do any management. You can just plug them into a switch in an expansion chassis and it just works. There's a number of devices that have been doing that for years. So the next thing is, let's say we want to do management. When you dig down and you talk to people, what does it mean to do JBOF management? What they'll tell you is, what it really boils down to is indicators. They want to be able to control indicators. So they want to be able to, assert a fault light associated with a drive or a RAID rebuild or so forth. So to address that issue, the NVMe Management Interface Working Group proposed NPEM, and this was basically a proposal submitted to the PCI SIG. And what NPEM is native PCIe enclosure management. And what it really boils down to is a standard mechanism for controlling indicators associated with drive slots. What this does is it provides a standard interface that OSs or management software can use to basically control indicators. So the OS can use this, software RAID applications can use this, and now you can blink lights on a JBOF. And for many applications, that's all you really need. Let's say that you want to build a real enclosure. An enclosure has power supplies that you want to monitor, fans, displays, and so forth. So now you need to do true enclosure management or comprehensive enclosure management. So the Management Interface Work Group looked at how do we do this management. And there were a number of options, one of which was we could go roll our own enclosure management. But what we realized is there's this thing called SCSI Enclosure Services, or SES. SES has been around for a number of years, been used to manage fiber channels, SAS. It's widely used in the industry, lots of tools. People are very familiar with it. If you drill into SES and you take a look at it and you take a look at what's inside, there's actually very little that's SCSI related inside of SES. What SES really deals with is how do you manage power supplies, control fans, displays, and so forth. So it basically has comprehensive enclosure management in a standardized way. So what the Management Interface Work Group did was standardize the interface from NVMe to SES. So you can now use NVMe SES in a completely standardized mechanism. So basically, to summarize, if all you want to do is expand drives, you don't need to do anything. The OS does it for you. If you want to blink LEDs, NPEM is for you. And if you want to have an enclosure with all the bells and whistles of what an enclosure has, you can use SES. All right, why would you want a PCIe JBOF? And I think this was alluded to earlier. Really, the point is latency. There are really two aspects of performance that people care about: bandwidth and latency. Bandwidth is easy. You need more bandwidth, you get a faster SerDes, you add more lanes in parallel. It's easy to solve bandwidth. Solving latency is difficult. And let's take a look at the advantage that PCIe offers in that space. All the way on the left is measured data for a flash SSD, which is the blue bar, and then basically the overhead of NVMe over fabrics on top of that. And what you see is that NVMe over fabrics in this real implementation adds about 10 microseconds of latency on top of an SSD. Now, we can argue whether that's 10 microseconds, 7 microseconds, or if you did a better implementation, is it 5? It doesn't really matter. The point is, that additional latency on top of a flash SSD is probably not a big deal, right? So it doesn't really matter that much. Where it really starts to matter is when you have faster SSDs. So think about Optane SSDs or Xenand or fast SLC SSDs that have a latency of 10 microseconds. That 10 microseconds of additional overhead now is 100% increase in latency. So that now becomes significant. And when you think about next-gen NVM and the latency that it'll offer of roughly 2 microseconds, that 10 microseconds of overhead is killer. So the real advantage of PCI Express is it eliminates latency. And it does this by getting rid of protocol translations. So on the left, we have a host. Virtually all hosts have PCIe interfaces. You've got to go through on a normal storage interconnect, you got to go to some sort of adapter, whether it's called an HBA or a NIC or whatever, that translates onto your fabric. You go through some fabric switches. You then need to translate back into PCIe, since today, all NVMe SSDs have PCIe. So there's two protocol translations. With PCIe, we get rid of those protocol translations, which reduce latency. But by getting rid of those protocol latencies, we get other advantages. We get lower cost, because now you don't need those components. And you get lower power, because you get rid of the power associated with those components as well. So that's the PCIe advantage. One of the challenges that you have with PCI JBOFs is sharing drives. So let's say you have a drive. Drives are becoming super high capacity now because NAND capacity continues to increase. And you need to be able to chop up that drive and share it across multiple hosts. There's a way to do that now, and the way to do it is with NVMe SRIOV. So SRIOV has been around for a long time. What's new is NVMe has standardized SRIOV. So what it's done is it's basically said there are a number of virtual functions. Virtual functions get mapped to VMs running on a hypervisor, and the VM can then have direct access to the virtual functions bypassing the VM or hypervisor. In NVMe, those virtual functions are NVMe controllers. So in your guest operating system, you can just run a standard NVMe driver and it works. The other thing that NVMe has done is it standardized the management of this SRIOV drive, or the PF, or physical function behavior. What that allows you to do is it allows you to write one physical function driver, and they basically plug in anybody's SRIOV NVMe SSD and have it work. So this is for hypervised environments, and this was really designed for that purpose. But with the proper switch software, we can basically take these SRIOV drives, and we can, with the switch software, map these VFs as true NVMe controllers to the hosts and allow a single drive to be shared. You can basically take the storage on a drive and slice it up and provide a slice to each host. Or you can have the host share the drives, and NVMe has reservations, so you can basically coordinate access to that. So with a PCI fabric, you can basically share drives. You can also do this patch panel functionality for composable systems, as was discussed earlier. All right. The final topic I'd like to cover is about CPUs and their place in the world. So in the past, when we talked about storage really meant having a CPU access persistent media. And it's been that way for a very long time. And the CPU has been the center of the universe. But now with accelerators and GPUs, the CPU is no longer becoming the center, is no longer the center of the universe. And some are saying even that these GPUs and accelerators are becoming even more important than the CPU itself. The challenge is, in today's systems, the memory associated with platforms is tied to the CPU. So if you want to do I/O, you got to go through the CPU to get to the memory, and that memory becomes a bottleneck. With NVMe CMBs and PCI JBOFs, you can basically eliminate that. So you can take a box, you can plug in GPUs and accelerators and a network interface, and now you can do direct network interface to SSD transfers and direct SSD to GPU transfers, bypassing the CPU and getting rid of the overhead. So the point is, it's not just a bunch of flash anymore, it's some flash and some other stuff, but that may be the way that systems look in the future. Thank you.
Hi, I'm Fazal. My background is I'm part of the team at Broadcom that makes an SoC that provides a fabrics interface into FBOFs, as we call them, fabrics attached JBOFs. And so what I'm going to show you is based on a lot of the customer interaction we have and what we're doing with our customers, how people are building those FBOFs. So what we see out there when we look at this whole FBOF, the whole NVMe fabrics market, we see it. There's a whole range of products that are out there that are being built, and they cover a lot of things. At the sort of what I would call the lower end of the market, you do what you call a SAS replacement market. Today when you put your hard drives in there, you use SAS for basically connecting all the drives together and connecting them into the CPU. And then, but at the other end of the market, where we're talking about things like the composable kind of architectures and scale-out kind of architectures, there's a lot more functionality on those FBOFs. People want to run TCP. We talked about TCP versus running a Rocky versus WiWarp. We see things like, because they're doing large-scale scale-out, they want to run TCP. They want to do things like IO determinism. As Peter mentioned, the drives are getting really big. You want to share them. Well, when you start sharing them, you start getting problems with interference between different applications. So what do you do about that? Well, that requires software on that side. So you see this sort of move from one end of the market to the other, and you also see that the types of boxes that they're building sort of are changing. If you look at today what people are doing, you do anywhere from this standard 2U box, which has 24 U.2s. That's a traditional enterprise kind of boxes. But then again, it was what Peter was showing is like Facebook does 30 to 60 M.2 drives in a small chassis, and they use M.2. They don't use U.2s. So there are different form factors depending on where you go and who's using it. And now this is also changing as people are looking at the limitations of the existing form factors. The existing form factors were a lot driven by what were the use cases were years ago. And now we're starting to look at where the use cases are, and people are moving to different. There's EDSFF is pushing new form factors all the way from the ruler, which is good for that SAS replacement market, and then on the other side of the higher end, we also see things like some of the EDSFF form factors. We're also seeing some new stuff about how do you do directly fabrics attached kind of modules. So I'm going to walk through a bunch of different sort of typical scenarios of what we see people are building. So if you look at the way FBOFs were done when we first started, when fabrics first came out, what people basically did was they took a JBOF and they put basically a server in front of it, and the server was connected to the PCIe to connect to the drives, and then it would run the fabric software, and then you would put a NIC on the front to talk to the network. So you put an RNIC for RDMA, you put an IWARP NIC for IWARP, or you put a regular NIC for TCP, but you ran it on a regular server. The problem with a regular server was it's very high power and it's very big. So what a lot of the companies that you're seeing now here, what we're all designing is different implementations of how do you get this into a smaller form factor, lower power, higher performance. So, for example, Broadcom does an SoC. Some of the other guys do SoCs. There's some people that are doing FPGAs. There are people that are doing ASICs that are very focused on just that market. So it ranges around. But we're all doing the same kinds of design. So this design is not about just one type of chip from one company, but about how the architectures are changing. So you'll see now, because these are now much more compact, a single chip is out there that does all this stuff. There's not multiple chips sitting there. So you can put a lot more of these inside a very small area and a very small power envelope. So this is a typical example of a high availability system. So people basically are building a couple of controller boards that they plug into the system to give them high availability. The cards have their own PCIe switch on there, and then there's a mid plane, and the drives are dual home to those mid planes. So that gives you one way of doing high availability. A lot of it is always driven about how you use the PCIe switches, because PCIe switches are the core of those designs, because everything is connected through that. So you typically, a PCIe switch is like a 96 lanes. So how do you map those 96 lanes? Is it 16 lanes to the SoC? You do a homing, how many lanes do you need for each, what kind of drives are you using at the back, and you use 2x2s or use 4x4s, but that's kind of typically on the U.2s or 2x2 that are dual home to the two controllers. So that's one typical example of a high availability kind of system. This is another design that we see where they really want, even here where you see the dual homing is to the two PCIe switches from each of the SoCs or ASICs. So if you have 16 lanes coming out of that device, 8 lanes will go to one PCIe switch, the other 8 lanes will go to the other PCIe switch. Here you can handle, even if the PCIe switch fails, you can recover from that. So that's another example of a high availability kind of model. And this is here showing extending that model to what happens in the network itself. So at the end of the day, between the client and that FBOF, you put Ethernet switches. I'll go back up to the previous one, you can go through one switch, but that's a single point of failure. So what you can do is you can dual home to the two switches, and that gets you around the single point of failure from the Ethernet switch. We see a lot of people that are basically building systems where those FBOFs are sitting there at the bottom of the rack, and they'll basically put two switches in the rack just for the networking, just for the storage traffic. Their data traffic that they use for talking out to the rest of the data center, that's a different switch. So they have a storage subsystem. Think of it as a SAN inside the rack, and then they have a data center network for all the other traffic. So that's the high availability kind of options. The other one that we see is, again, now it's back to where is it going in places where we have a lot of customers that don't care about high availability. If you're doing things like you're doing, for one, the hyperscale guys, what they do is they replicate data across their data center. So they don't want to manage high availability. What happens if the switches fail? Because that adds complexity to their whole management scheme. It's easier for them to just replicate data three-way across the data center or even across data centers. So they just want simple connectivity into the network. And so that tends to be the drives are just connected directly to the PCIe switch into the SoC or ASIC and out to the network. That's really what they end up doing on that one. And also what that allows them to do is they don't need dual home drives, which tend to be more expensive than single home drives. So that reduces cost for them. And since they deploy at scale, cost matters. And the last one is one of the other things that we're seeing right now in the cloud space, and is that people are starting to ask themselves a question about, oops, what happened there? They're starting to ask themselves the question about, why do I need to build this box with this FBOF box, which was basically a JBOF that I've attached the fabrics interface to it? Why don't I break the problem down differently? And this is an architecture that we're seeing out there where basically people are saying, take the SoC or the ASIC and connect the drives directly to it. The field replaceable unit now is that whole module. It's an Ethernet-based field replaceable unit. You don't need to worry about, you're not pulling drives in and out of PCIe, you're pulling the whole module out of it. The model being, you've taken a drive that's a 2 terabyte drive, you put 4 or 8 of these on there, you get, 16, 32 terabytes. That's how much you're replacing at one time. So you have 16, 32 terabytes in a module. Something fails, you replace that whole module. If you're worried about what happens, again, back to the cloud kind of environment, they're replicating that data somewhere else in another rack anyway. So it's easy for them. Ethernet is really easy to replace. I mean, people do that all the time. It's been there forever, and that works really nicely. So we're seeing that actually there is if you guys go into the WD booth, they have a module that basically does something like that. They have a module that comes out, it's just fabrics attached, pull out the drive. You plug it in, plug in your Ethernet on the other side, that's it. And all you know is you have a fabrics attached device with X amount of gigabytes on it. So that was pretty much it.
Yeah. Thanks, Fazil. My name is Sujoy Sen. I'm from Intel. And so we got a pretty good overview of different kind of JBOF and FBOF architectures, the market opportunity. Certainly, I think we have a good handle on where this is going to go in the enterprise space, both from a use case standpoint, a business model standpoint. We also, I feel, the ecosystem around fabric-attached JBOFs is developing very rapidly. We have a lot of players now, providing controllers, Ethernet controllers, JBOF controllers. But if we have to go make them successful in the cloud, I think there are other problems that we need to solve. And since I sort of work in pathfinding, my job is to look for problems, kind of a depressing job, but there you have it. So I thought, I'll finish this session, this set of presentations with, sort of challenges that I see that we as an industry need to go address if we want to make this successful, this FBOFs. Whether a full enclosure or like what Fazil was showing, modules, but essentially, this disaggregated and composable use case that Brian talked about. If you want to make it successful in the cloud, what do we have to do? And when I say cloud, I'm really talking about scale. Anything that's at large scale or aspirationally, wants to get to a large scale, a large number of compute nodes, large number of storage nodes, lot of network switches and hops in between, basically thousands of nodes. And even though life is more nuanced, you always have to distill everything to three things. And that's what I try to, sort of distill it down to three challenges. And I'm sure there's a lot more, but it just seems like these three, most of the others fall into one of these three categories. The first one is really network quality of service. And Nishant talked a lot about RDMA, congestion problems with Rocky V2, the TCP coming down the pipeline. And all of them, all of that's good stuff, right? But, while the network is, the FBOF's best friend, right? It allows the accessibility to storage, from anywhere. But it's also its worst enemy, because if the network doesn't perform, then the FBOF is just an expensive piece of metal, right? And it's not even made of platinum, so, you can't do anything else with it. And when I say network performance, it's really all about consistent performance and low tail latency, right? Peter mentioned, latencies with PCIe. I mean, PCIe not only performs, delivers low latency, but delivers fairly consistent latency, right? But that's not true for regular networks, especially when you scale it up, right? And then especially now if you go with RDMA and Rocky, congestion can become an even bigger problem, right? And then in trying to control that congestion, management becomes a big problem, right? You can tune a small network fairly well, right? You can configure switch buffers, and you can configure NIC buffers and queues and things like that, such that you can manage ingress rate, egress rate quite nicely, but not so much in large networks. So I think that's an area that's ripe for attention, right? The other two, and I have a little more details on the other two in the following two slides. But the second one is really, it needs to be very easy to deploy. Again, because it's at scale, we're not talking about a few JBOFs and a few hundred compute nodes that consume the services that the FBOFs provide. We're talking about thousands and thousands of nodes, right? So it needs to be easy to deploy and easy to manage from an operational standpoint. And last but not the least, when we talk about the cloud, and Brian referred to this as well, there is obviously large scale, compute nodes, that directly need sort of NVMe services. But there's also cloud storage, which is typically shared nothing distributed scale out storage. And, they're not designed and architected to be friendly to disaggregation, right? Not today. And we need to look at how to make that friendly, right, to FBOFs. So on the ease of use topic, really what needs to happen is we have to do an end-to-end management. And end-to-end is a very used word. Everybody wants to end-to-end something, right? But in this case, it truly has to be end-to-end. I mean, managing a JBOF is just one part of it, right? And for the most part, we understand how to do it, right? Peter referred to all the enclosure management work that's going on. But it's not just managing the JBOF. It's discovering them, provisioning them, monitoring them at scale, right? When you have hundreds of them. Right? And then once you manage the JBOF, that's not good enough, right? Because if you're going to do composed storage, that means the host that's going to consume that storage needs to be provisioned correctly as and when you're composing and decomposing that storage. That means you need something on the host. And mind you have 100,000 hosts, right, in a Microsoft data center, for example, right? How do you do that, right? How do you, how do you do that at reasonable speeds, for example? How do you do that when the operating system and the storage stack that's running on that host isn't something you own or you even trust? So certainly it's a challenge, right? And then there's the network in between. I talked about that a little bit earlier, about how, you manage the JBOF, you provisioned it, you created volumes, namespaces, everything out of it, you composed it, you attached that to a host, you configured the host, but now you need to configure the pipe correctly, right? And monitor it and make sure your SLAs are getting met. So that's what I mean by end-to-end, right? All these three elements have to be managed correctly. So one way, there's sort of two ways to, well, I shouldn't say two ways, two sort of use cases, right? One is where a cloud OS is running, like an OpenStack or Kubernetes or VMware, who have already, to some extent are solving the problem of managing lots of hosts. So, but they treat NVMe devices as static, locally attached devices, even though it may be surfaced up from a network-attached FBOF. And that needs to change, right? Those cloud OSs have to natively understand what NVMe-oF is, that NVMe storage could be networked and shared as well as they need to understand what composability, dynamic attach, detach, reconfiguration means. Right? We at Intel are doing some work with OpenStack and Kubernetes in this front, but certainly a bunch of work has to be done there. And the third thing is bare metal. So when you're not running a cloud OS, you're renting out the entire server to a tenant. You still need to be able to compose storage on it, right? So you can do it, you can do it via a hardware initiator like an HBA, and you can manage the HBA. Or if it's a soft initiator, the OS and the server platform itself needs to be able to surface information about, its targets and things it should talk to, in a platform independent standard manner, right? So something that a soft initiator can pick up and just run with it. Again, in the RSD world, we are doing some work around this area, but certainly something that I think server vendors should look at, OS vendors should look at as well. And my last thing I wanted to sort of talk about was the scale-out distributed storage. Again, there's, if you can disaggregate the media from these storage service nodes, there is a lot of benefit. Brian touched upon the utilization, independent scaling of compute and capacity. But fundamentally, these storage services are not architected for this kind of deployment, right? The first problem is you have a blast radius and failure domain problem, right? You have, the storage nodes expect that the storage they see, the physical storage they see, is local. If that fails, they only have to recover from that point of, from that disk's perspective. But if an entire JBOF fails, and you may have an HA capable JBOF, so you eliminate or reduce the possibility of its failure. But if it fails, it can take out a lot of nodes, right? More importantly, there's more probability of soft errors, right? Because you have the network in between. There could be jitter. There could be things that causes the storage software running in the service nodes to think that the media is behaving badly. So you really need a unified management system where the distributed storage service knows the fact that it's running against a disaggregated storage and deals with it accordingly, right? Deals with errors in a more, soft and friendly way rather than in a hard way. Right? You need to be able to manage this such that when you allocate, resources from a JBOF into the storage node, you take into account failure domains, right? So you don't have, multiple. You reduce the probability of multiple failures at the same time. The second one is, today the partition between the distributed storage nodes and the JBOF is really a block NVMe interface, right? And maybe that's not the right interface, right? Maybe that has to be, enhanced such that, you partition it such that some of the more media-centric activities that the storage nodes do today is done at the JBOF, right? But not everything, because then you're just replacing the storage node, right? But things like managing the data layout, managing the media, managing some level of replication in HA perhaps, compression and security, those things you can sort of offload into this JBOF. So this partitioning is something that we should all look at and see if, what makes sense. You also reduce network traffic when you do that, right? And last but not the least, NVMe fabric itself, perhaps needs to be extended to be more cluster aware, right? Not be very NVMe controller and disk centric, right? In order to sort of start participating in this sort of architecture. So yeah, that's all I had. So I thought, I basically posed a bunch of questions. I don't have answers to any of these. So I'm just hoping somebody comes and says, I know how to solve these. Thank you.
Okay, so thanks everyone. A lot of information there for sure. Just to summarize very quickly, hopefully you've seen how JBOFs and EBOFs can be built and used in various applications here, as opposed to things like storage appliances or arrays, enterprise class arrays. We've seen a couple of different options and some pluses and minuses for each. PCI Express Direct Attach, great for in the rack. Limited by distance, but superior in terms of performance and latency. And then the expanded capabilities you get with a fabric-attached FBOF, so that you can scale at the level of Ethernet or fiber channel in terms of both distance and fan out. And some management opportunities. We have a lot of hardware now coming to market this year that enables these various EBOF flavors, and now it's time to provide some software solutions that allow these to be composed and put into real work environments here. So it's an exciting time in the evolution of data center architecture here, I think. So that we're out of time here effectively, but I'm sure we can squeeze in a question or two if there's anything pressing. So anybody? Oh, sorry. Thank you. Yes.
So in terms of fabrics, you talk about advanced RDMA-based PCle Advantage.
Sure. Yeah. Did everyone hear that? Amongst RDMA on Ethernet, there's different flavors. Rocky versus iWarp. Rocky seems to be getting more traction. What are the advantages of that versus, say, iWarp or non-RDMA? So I'll take a shot at that, unless you guys want. No doubt there are more vendors putting Rocky RNICs out there than iWarp, but iWarp is available from at least a couple different vendors. My perspective is that iWarp tends to work better in a congested environment, or maybe a more lossy environment, so there are advantages there. In terms of RDMA versus non, the beautiful thing about RDMA is that the interaction on the application side does very little. It launches out a command and then it gets an interrupt at the very end when the data has been placed there into its buffers. With some of the non-RDMA protocols like Fiber Channel or TCP, the OS is going to have to be involved with the driver as it's receiving that data and then pushing that up and placing that into the application's buffers. So those are some of the trade-offs. Performance being one of the key differentiators between RDMA and non. Anything?
Yeah, I think our perspective is very similar to what Brian said, which is there's a lot of ONIC vendors out there, and we all pushed Rocky. And I think that's where the traction came from compared to some of the other approaches. As far as TCP is concerned, I mean, the spec is not even done yet. The spec is, the expectations right now sometime before the end of the year will be done. And last year you saw like one vendor showing TCP at the FMS. I think this year there's like 3 or 4. So I think TCP came later But I think there's a class of people that will use TCP because they don't have to worry about all this congestion stuff, making changes on their servers. I mean, if you use an ONIC or even iWarp, you have to put a special NIC in your server. So for those customers who want to have control within the kernel and or don't want to change hardware, but latency is not the highest thing on their list, at least network latency is not the highest thing on their list, then they'll mostly go to TCP. But TCP is, because of the standardization, can happen later.
Anything else? Okay, well, thanks for attending. Appreciate you listening to this, and we're all available for more information. I think I have, some contact information. These slides will be published along with everything else here at FMS, so you know how to get in touch with any of us for follow-up. Thanks, and enjoy the rest of the show.